Okay, so we're going to look at discrete Fourier transform. Fast. It's also called FFT, and we'll see some applications for string matching for polynomial multiplications and stuff. So you would have seen, Fourier analysis in some signal processing kind of context, which is transforming some signals into frequencies or something. Here also we will be transforming a vector into a different vector. We'll see what it is. So let me start with polynomial multiplication, because that's the motivation for this, and then we'll get to FFT. So here also we will use divide and conquer based algorithm, but it's not an involved divide and conquer like what we saw in finding the median. Here it's going to be simply like a merge sort kind of a recurrence, but the problem is interesting and useful. So we'll see. So what is you're given two polynomials over some complex field, of degree n, we want to multiply them, right? Or compute ax times bx, because these are the coefficients are coming from some field, let's say it's some complex numbers, and we want to multiply these two polynomials. We want an efficient algorithm for this problem. Okay. So the standard multiplication based on the definition of the product, how much time would it take? In square, because so the product will have degree 2n minus 2. So let's say I have summation I going from 0 to 2n minus 2. And what is the coefficient of x power I? Well, you pick some j from the A polynomial and the remaining I minus j from the B polynomial and multiply, right? So Aj, okay, into B I minus j, right? So if I want the coefficient of x cubed, then it will be A0 B3 plus A1 B2 plus A2 B1. Okay, that's what I've written down here. So in the worst case, computing each of these coefficients could take up to order n times, so it will be n square. Right? Okay, what are we counting? We are counting these kind of multiplications. Okay, and the goal is to get an n log n algorithm for this. Multiply two polynomials of degree n. So let's you can also talk about adding two polynomials. That's pretty easy because you just have to add the coefficient. That's a linear time operation. Okay, so the way we will get a faster algorithm is by moving to a different representation of the polynomial or the polynomials, And what is this representation? It's the point value representation. So we'll fix some. So basically, these polynomials are uniquely determined if you know their values on n different points, right? It's there are n unknown coefficients, so you will have a matrix or a linear set of n linear equations. You solve them, you will get the coefficients. So if I know n distinct, so we'll fix some n distinct points. Let's say x1, x2, xn. So my representation for ax would be x1 comma ax1 and xn comma axn. And similarly for bx would be, okay, so yeah, okay. And representation for bx would be on the same x1 to xn, I evaluate my b values, b polynomial, and I get these. So is it clear that you can actually go back and forth, that's unique? How do you argue that if I know this polynomial on n different values, then I get a unique polynomial that satisfies these constraints? Write down your equation. So if I have, okay, so let axi, let me denote it by some yi. Then what do I have? I have a0 plus a1 x1 plus a2 x2 plus an minus 1 x power n minus 1 is y1. Dot 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 a0 plus a1 xn plus a2 squared. Yeah. So n different equations on n unknowns, a0 to an minus 1. Why should I have a unique solution? When do I have the unique solution? So write down this as in the matrix form where I have 1 x1 x1 square times a0 a1 up. Okay, I could have written, yeah, it's fine. Right, it's a metric equation. This matrix times this vector is equal to this vector, and you are given this vector. When does it have a unique solution? If this matrix is invertible. And is it invertible? Yes, because what is it? Do you know the determinant of this matrix? Right, it's a special matrix. It's called Vanderman's matrix, and its determinant of this matrix is product xi minus xj, I less than j or something. And since all the xi's are distinct, I have this product which is non-zero. So you can compute the inverse and compute your ai's by this inverse times the yi's. Okay. So, this is how you can go from here to here and come back from there to here. Okay, how do I go from here to there? Well, evaluate your polynomial on all these n distinct numbers and you get this yi's. So, why is this representation useful? Now, if I want to compute product of two polynomials in this representation, how much time does it take? Order n, right? Because I just have to evaluate this polynomial on this n distinct numbers and I just have to multiply, right? Because the product a times b on x1 is ax1 times bx1. So, you just have to multiply pointwise and I can do it in linear time. There is one little catch. So some any n distinct points. We will come back to what these points are, but for now, some arbitrary n distinct points in your field. And just go and evaluate. All I care about is that they are distinct, so that the determinant is. Yes. So each polynomial, I evaluated at x1 and I get ax1. Evaluated at x2 and I get ax2. So I evaluate this polynomial, and how much time does it take to evaluate and all that? We'll come to that. But let me just look at this representation. And so these n distinct points are fixed. Now, if I want to multiply, I have these polynomials in this kind of, I don't know the a coefficients, right? I have been given in this representation, and I want the product polynomial in this representation. What does that mean? I want the value of this product polynomial on this n different points. So, just pointwise take these values and multiply them. So, you can do it in linear time. So, what is the catch? Why not? Because yes, so your product polynomial has degree 2n minus 2, but so it's not enough to evaluate it just as n points. So, to fix that, what we will do is just evaluate it at 2n distinct points or 2n minus 2 distinct points to start with. So, even a I would evaluate it at 2n different distinct points. There is some redundancy here, but that's okay. It's useful when I do the multiplications, right? So, because to retrieve back my coefficient, or to have this unique representation, I need this polynomial to be evaluated in as many different points as the unknown coefficients are. Okay, and so since the product polynomial can have degree 2n minus 2, there will be 2n minus 1 distinct coefficients. So, to start with, even a and b, I evaluate them in 2n distinct points, so that when I do the multiplication, I can do in pointwise form. So, the good thing is that if you are given polynomials in this form, with this extended 2n distinct points, then I can evaluate the product in linear time. Okay, how much time does it take to go from here to there? Well, to evaluate this polynomial in one point is going to take you some order n time, right? You can use some Horner's rule. You don't have to take x power n minus 1 or x power everything all the time. So, you just have to, so you can do it in linear time to evaluate a at one point. Now, you are evaluating it n different points, order n different points. So, you need n square time to go from here to there, right, for each of these polynomials. And to get back from here to here, you need to compute the inverse of this function. Okay. In general, if you have to compute the inverse of a matrix, the standard Gaussian elimination based algorithm will take something like an n cube time, but there are faster algorithms. But this is a special matrix and you can evaluate its inverse in n square time. Okay. Let me just write it here. So, inverse actually has even a formula. Okay, so the bottom line is that if you are given in this form, no problem, you can compute the product in linear time. But if I am given the polynomial in this form, which is usually the case, then to go there to compute the product and to come back here would take n square time if I'm doing it this way, right? You know, if I'm going to spend n square, I might as well do this. So how do we do it faster, right? So now the way we can do faster is we will exploit the fact that you can evaluate this in some any 2n distinct points. So we will choose certain set of points to evaluate, which will be faster. We can do it faster than n square time. Not only going from here to here, but also going from here to here. We can do it in n log n time. Okay, so it's going to be some divide and conquer, merge sort kind of a recurrence. So what are the points on which we are going to evaluate these polynomials? And for that, we're going to go to some complex numbers and roots of unity and understand the properties of them. Okay, so right, so the goal is to evaluate, and the reverse process is called interpolate the polynomials, or we'll work with one polynomial because if you're doing two polynomials, everything will be doubled in n distinct points in order n log n time. This n is really 2n for us, okay, because you need to evaluate at 2n different points, but I'm going to call it as n. So what points are we going to use? We will use complex nth roots of unity. Hopefully you've all seen this, but you would not have imagined that it will have some application here, but we will quickly refresh what they are and what their properties are, and then we'll get on with how fast we can evaluate, right? So the complex nth roots of unity are one when we denoting by omega n square, and this is called the principal nth root of unity, and which is e power 2 pi I by n, and we can use this formula that, because these are complex numbers, and I said, we're going to be working with this complex field. So what do we know? This set of numbers form a group under multiplication. So everybody has an inverse, they're closed under multiplication, and it sort of simulates. So if you take the exponents, they form a group under addition modulo n, okay, because it's omega n power 0, omega n power 1, 2 up to n minus 1, and if you multiply again, it's omega n power n will become 1, so omega, so the product I times j is I plus j mod n, okay, so they form a group. Okay, and we need some other properties because we are going to use a divide and conquer algorithm to compute. So these are the endpoints on which we are going to evaluate our polynomial. Yeah, that's the complex square root of minus 1. It's the same as this I. And this I. Okay, so okay, so let's come back here and how I'm going to evaluate, and then we will see that these complex roots naturally have some nice properties for us to evaluate our polynomial. So what is the discrete? So you can think of it as given a0, a1, an minus 1. This is our polynomial represented by this coefficient, and we are transforming this to y0, y1. And what are these? This is exactly the value. So yi. Okay, what are these? These are the evaluation of these polynomial on these endpoints. Okay, so yi would be evaluate this polynomial at omega n power I. Okay, so it's transforming one vector into another vector. So that's the Fourier transform. Okay, and we are evaluating at this specific complex nth root of unity and whatever vector, and we will also see that we can compute the inverse also in n log n time. Okay, so this is the discrete Fourier transform. Yeah. These are okay. So there are some issues about when you are trying to implement rounding and things like that. We are not going to deal with it now. Maybe I will next time, but for now it's a nice mathematical concept and an algorithm. Okay. So this is the discrete Fourier transform, which takes this vector A and gives this vector, which is evaluating this polynomial a0 plus a1 x plus an minus 1 x power n minus 1 on these n values. Okay, so let me write this polynomial in a way for computing, for using divide and conquer. So another thing I'm going to assume n is a power of 2. So these discrete Fourier transforms, they are defined for larger other n's as well, but that is more complicated. So we're going to assume n is a power of 2. Or n minus 1 is a power of 2. We'll see what I needed. So let me pick up the even coefficients. And the odd coefficient. No, is it n minus 1 by 2? Is it again n minus 2 by 2? Yeah, okay. both can't be right. So n, what do I need for n? Okay, so what is the last term? Did I get that right? Yeah, yep. So did I get the? No, I'm writing only a2x for now. So n minus 2 is even, that's correct. So n minus 2 by 2, okay. So a1 plus a3x. So it's not 3, oh, n minus 2 by 2. I think that should. No. Yeah. Right. So if it's a3, it's 3 minus 1 by 2. So that's a power 5, 5 minus 1 by 2. So for n minus 1, it's n minus 1 minus 1 by 2. Okay. Because n is even. So we have assumed n is a power of 2. Okay. So now, can you tell me how do I write? So one good thing is that both these are polynomials of half the degree. So I'm all ready to now apply, recursion, divide and conquer kind of thing. So what is a of x? A of x is a0 of x square plus x, ae of x square yes. So ae of x square is fine because it's a0 plus a2 x square plus a power 4, a4 x power 4 and an minus 2x. This is exactly the original polynomial. Now a0 of x square, this will give me a3 x square only, but a3 should be x cubed. So I'm multiplying by an x outside and that takes care of it, right? So what I have now is two polynomials of degree half the degree, but if I have to evaluate a at x, x1, x2 up to xn minus 1, but ae, I mean these guys I need to evaluate them at x1 square, x2 square and so on. And similarly here, yeah, okay. And turns out that nice property of nth roots of unity are pretty useful for me to evaluate these guys recursively. I mean, what do I need? So if I want to evaluate a at nth roots of unity, if I want to apply recursion, I want to be able to evaluate ae and ao, which are half the degrees, at n by 2th roots of unity, right? If that's what my recursive subproblem is, then I am all ready to do divide and conquer and put them together, right? And it turns out, and that's all we will show in the next few lines, that if you have this guy's nth roots of unity, when you square them, they turn out to be n by 2th roots of unity. And that's all, and more or less that's the end of the story, okay? But we'll just go and prove that. And then the other thing we need to do is to do the interpolation as well, that inverse problem as well. Okay, so what are some properties of this we want? So omega n dn dk is the same as, that is dkth power of dnth roots of unity is the same as kth power of nth root of unity. Okay, so for all d greater than or equal to 1. You just have to apply this formula, right? Omega n is basically 2 pi I by n. So omega dn would be, you will have a d here, and you're going to multiply, take the whole thing power dk, d will cancel out. So it will be just this whole thing power k, right? That clear? Okay. So corollary of this would be that, what do I get? Right? If you look at the omega n by 2 here, halfway point, what do I get? Well, think of this as 2 times n by 2 and 1 times n by 2. So d is n by 2. So I'm going to cancel out n by 2, and so this will be, or you can just plug it into the formula and see what you get. It will be basically e power pi I, and e power pi I from this formula is cos pi plus I sin pi. As this thing will vanish and this will become minus 1. So this is minus 1. So what this says is that the halfway point, what you get is minus 1. So after that, because of this multiplicative group business, you will have all these guys appearing in the minus in this. Okay, so that's why when you square, they become the same essentially. So let me just write this. So basically, what that means is omega n k plus n by 2 is minus omega n k, right? Because omega n power n by 2 is minus 1. So it's minus 1 into omega n power k, and that's what it is. And this also means when I do the square, okay, so that's more or less it, right? So what am I saying? That if you take these values and square them, each one of them, what happens is this term, basically, you have the second half the same as the first half. That's what this is saying. After n by 2, it is the same as, omega n k square. Okay, and yes. And the next property what I want is 1 omega n square omega n power 4. Basically, I take these terms and square them up. Right, the half the guys. They form n by 2 roots of unity. Because this term by my property 1 is the same as omega n by 2 1. And this term would be omega n by 2 square and so on. Okay, that's it. So now, if I want to evaluate A at n complex nth roots of unity, what you do is evaluate AE at complex n by 2th roots of unity, because the squares of these guys are exactly n by 2th roots of unity. Similarly, evaluate AO at complex nth roots of n by 2th roots of unity, and they are of half the degree anyway, and put this together, because so x will change, right? So, and you have to multiply this by x. So that's it. So let me complete the algorithm now. Yes. Okay, so I think it is. So algorithm to compute AX for x equal to 1 omega n. This is what I want. Step 1, recursively compute AE at 1 omega n by 2 square and also A at these points. Okay, so let's say these guys are y1, y2, y and n by 2 minus 1. Okay, so this is y0, which is AE of 1, and this is y1, which is AE of omega n by 2, and so on. Recursively compute AO at 1 omega n by 2, and let there be z1, z2, and zn by 2 minus 1, z0, right? Yeah. I've computed these guys recursively, so it's 2tn by 2. Now I will say that to get my A at these points, okay, so let me erase this. And my step 3. I want to evaluate A at this point. I would just say it's AE at, which I've already computed, plus x, which is this, into A odd at and for I going from n by 2 to n minus 1, a actually for everything it's plus only. So why do I even want to separate this? Yeah. Okay, why do I want to separate it? There is a reason. Because these guys are computed only for n by 2 different i's, not n different i's. So when I want I to be some n by 2 plus something, I don't have that value here, but I know that it is the same as do mod n by 2 and whatever value you get, that's the same I. Okay. So another way to do it is just compute for the first n by 2, it will be this, and the next n by 2 you will have a minus here because omega n by 2 plus I is the same as minus omega n I. Okay, so yeah, I think this is still fine. So is it clear? Are there any questions? So
we are talking about some 2n points.
yeah. So I said my n is 2n, right? The starting
Then we were mapping from some
2n roots of unity, 2n points. Start with evaluating my polynomial on 2n roots of unity. My n here is actually the 2n I needed. Okay, so the whole thing just doubles, right?
I have one more question. Why did you change to n by 2 to n minus 2?
No, so what is my goal? I want to evaluate a at these n different points. That's my goal, right? And I have just written my a of x is ae x square plus x times a0 x square. But wn I square is the same as wn by 2I. That's why it's enough to evaluate it here, and that's the same story here. Okay, but the x remains x. This is not square, so x is the same. Okay, now why was I having this confusion? I said, remember you were evaluating ae at 1 omega n by 2 omega n by 2 square up to omega n by 2 minus 1, right? Because you are evaluating only at n by 2 points, but here I am just going beyond n by 2 also. So where do I get the value omega n by 2 of n by 2 plus something? Well, these guys report it's modulo computation. So omega n by 2. So if I want omega n by 2, because this is computed only up to n by 2, but after n by 2 it's going to repeat because of this group properties. So it is well defined. So after n by 2, it turns out to be the same as do a mod n by 2 and whatever the remainder, and that's already computed. So that's the only thing to be careful about. Okay, and how much time have I spent? Well, 2t(n by 2) because these are polynomials of half the degree on evaluated at half the number of points, and then I'm spending a for loop which these are computed values. I'm just adding it, two numbers, adding it, multiplying by a complex number and so on. So this is, of course, if n is small, you do it something very simply to your multiplication. So we had all the nice properties of this nth roots of unity. In particular, the squares of these guys turn out to be n by 2th roots of unity repeated twice. So That's the main property which is useful to do this divide and recursive divide and conquer. Now, so if I am given two arbitrary polynomials in the coefficient form, I can turn to this point value representation in n log n time, where the points I chose are the 2nth roots of unity. Okay. Okay. So now I want to come back here to the point value, to the coefficient representation for the product, right. So I go here. So given A, I compute A at these points in n log n time. Given B, I compute B at these points in n log n time, and then do a pointwise multiplication to get the product at these two endpoints in linear time. Now I want to come back to the coefficient representation. Okay. So let's look at that part of the algorithm. So it turns out that is also very similar to evaluating at some nth roots of unity. Okay. So the inverse problem, right. What is this? Given yi equal to a, I have given you the values of these polynomials at these n different points. Now compute the coefficients. Right. So my a0, a1, a minus 1, where a of x is a0 plus. Because ultimately your input is given in this coefficient form and I want the product in the coefficient form. So you evaluate, go there, compute the product at these endpoints. Now I want to get back to the coefficients. Okay. Okay, so what is given to me is that this matrix again, the Vanderman's matrix 1, okay, so what is this matrix? So I'm evaluating first at Wn. No, I'm evaluating first at 1. So when I evaluate it at 1, I will get 1, 1, 1, 1, 1, right? Then I'm evaluating at omega n square. And so that's this matrix. Right? So you're given that this times a0 to n minus 1, this column vector is equal to this column vector, and I'm interested in the inverse of this polynomial. So let's call this, sorry, inverse of this matrix. Let's call this matrix is D. where what is dij? I going from 0 to n minus 1, j going from 0 to n minus 1. I into j plus 1. I into j, is it? Yes, okay. Yeah, I into j, right? The 0th row and 0th column all get 1. And if you pick, let's say, the 3rd row, this is 0, 1, 2, 3. No, this is the 2nd row actually, 0, 1, 2. Yeah, 2 into 3. So, wn I into j. Now, I am just going to claim the ijth entry of the inverse matrix, and then we will prove that this product is actually identity or something. Okay. So, the claim is dij inverse minus j into I. Yeah. Okay, so once I show that, then you realize that then it's essentially computing again some sort of a Fourier transform of these vector, right? Because you are evaluating. So what we will say is that take this vector and multiply by this matrix defined by this, and I am going to tell you that you will get the AIs. Okay. So it is like another Fourier transform computation, because the ijth entry looks very much like, instead of wn ij, it's minus ji. So you just have to do wn power minus 1. You take that minus 1 and instead of evaluating it as 1 omega n square omega n minus 1, you will evaluate it as 1 omega n power minus 1 omega n power minus 2 and so on. Okay. What omega n power minus means? It's just the inverse of the other one. Because of this group, you have you can think of it as n minus, right? Omega n power n is 1. Okay, so now I'm going to prove this. So how do I show? We will show that if you take d into d inverse and look at the ijth entry, this is equal to 1 if I equal to j and 0 otherwise. Right? That will show that what I have is actually inverse of that matrix. Okay. This is yet another property of this complex nth roots of unity, some very simple property. We will use that and show this. But so is it clear that if I show, then computing d inverse or computing the AIs, okay. So let me actually get on to proving this. So let's see, and then we'll see. So what is this? So summation dik into d inverse kj, right? K going from 0 to n minus 1, right? What is the ijth entry of the product matrix? You take the ith row and jth column and multiply pointwise, right? Ik into kj. Well, what is dik? Well, I have written down here omega n power ik. Yes, and the inverse of kj, I have written down here, it's minus by n. This is equal to 1 by n into summation omega n k into I minus j, where k goes from 0 to n minus 1. So when I is equal to j, each of these terms is 1. There are n terms here. So when you divide by n, it becomes 1, right? So is equal to 1 if I is equal to j. And if I is not equal to j, property of complex nth roots of unity, this thing vanishes. Okay. So let's see what is that property I need. Generally, what do I need? Summation some kd, where k ranges from 0 to n minus 1 is equal to 0 as long as d is not congruent to 0 mod n. Yes, right. When d is congruent to 0 mod n, what is this? This is 1, because you have a multiple of n there, omega n power n is 1. So this whole thing is 1. But otherwise, whenever you are multiplying by something which is not a multiple of n, I want to claim that this sum, the summation is over k, vanishes. Okay, and here I minus j is, we are going to use the fact that it is, if I is not equal to j, since I is ranging from 0 to n minus 1 and j is ranging from, so it's at most n minus 1 to minus n minus 1 or something, right? So it's not a multiple of n, this I minus j, and so whenever I and j are not 0, not equal, this term vanishes. Okay, what is the proof of this? It's just simple geometric series proof. What you have omega n power d as the common ratio, and you're summing over geometrics, and whatever formula you've seen it for geometric series sum holds even for complex numbers. So we have this is equal to omega n d whole power n minus 1 . Since d is not a multiple of n, this term is not 0, denominator is not 0, but the numerator is simply because this is 1. Okay, so net what do I get? The inverse of the matrix, this matrix is defined like this. Question. Sorry, I meant D not equal to, not 1. Thank you. Because D is a multiple of 0, then this becomes 1. Yeah. So now let's see, how does D inverse look like? So what we are saying is that my goal is to compute the coefficients given the yi's, right? So all I'm saying is that take your inverse of this matrix, multiply by y's, and you get a's. And what is the inverse of the matrix? Dij inverse is defined like this. So maybe I'll write a 1 by n at the outside. So when I are 0, j are 0, this is 1, 1, 1. And when I is 1 and j is 1, I get this would be. So this matrix looks pretty much like this matrix, except instead of I'll have a -1 at the top. That's it, right? So this is exactly like evaluating your polynomial y0 plus y1x plus yn minus 1 xn minus 1. You want to evaluate them at these points, omega n power -1, omega n minus 2, omega n power minus n minus 1, and do exactly the same thing what we did. Instead of omega n, do omega n power inverse. We will have the same kind of properties of divide and conquer, recursive, all that, and you can get in n log n time. Okay, so the same as evaluating y0 plus y1x plus -1 is same as n minus 1, right? So it's the same thing. It's exactly the same thing actually. If you just think of it, it's just in a reverse order. So we know how to do this in n log n time, right? Now we have a different polynomial. Okay, to summarize now, we want to compute two polynomials of degree up to n minus degree up to n. So you are given ax, bx, evaluate at, if they are of degree n, then I will evaluate it at 2 nth roots of and similarly evaluate at these points, and we can do it in n log n time using this divide and conquer. And then you come back, compute the product axi into bxi for and this takes order n time because this pointwise multiplication, and then do your inverse, come back to get so this takes n log n time. So it's n log n plus this order n plus this n log n. So okay, and that's all. So this has a lot of other applications. For example, you can imagine multiplying two integers, two n-digit numbers, as evaluating a polynomial, right? So because if you have a number n, which is in decimal, you are written it as a1 to an minus 1. What is the value of n? It's okay. So maybe I put a0 here and an minus 1 here. Then it's an minus 1 into 10 power n minus 1 plus an minus 2 into 10 power n minus 2. Right? It's essentially two different polynomials. Instead of x, you have this 10. Okay. So if you can compute the product polynomial and plug in your value 10, what you get is the product of these two numbers. Okay. Okay, so there are lots of issues here. So first of all, it has several applications. We will see some very surprising application for this fast Fourier transform for string matching algorithms. It has applications for integer multiplications, and there are also other issues about representation, right? That we are evaluating at complex numbers. So if I want to really go and implement and write these terms, they have rounding values because these are real numbers. You can write complex number as two real numbers, but real numbers has some rounding issues. So there are ways around it because you just go and do everything modulo a finite field or something, where you can represent the numbers compactly. And so there's been a lot of work on those directions, and just the integer multiplication itself, right? We saw this n power log 3 algorithm by just taking two n-digit multiplication, recursiving into 3, but you can just go and feed it into these polynomial multiplications and use them. And currently, the current best algorithm for multiplying two n-digit numbers stands at n log n log something. They all have this similar flavor of applying this fast Fourier transform somewhere in between and doing something. Okay, so this is it's not completely resolved, and we don't know whether that is the best integer multiplication algorithm or not. Okay, so this is just yet another application of divide and conquer, but it uses complex nth roots of unity to multiply two polynomials. Okay, we'll see other applications next time.